Okay, so this week we will talk about shrinkage methods, which is the alternative way of doing variable selection, which we talked about last week. Remember, we did best subset selection, and we also did stepwise selection by comparing different models to look at their look at different criteria to compare those models. And this week, we will basically focus on Ridge Regression and lasso. They are the two most popular basic shrinkage methods. Let's see. Okay, so as I said, they are alternative to select variables. And the shrinkage methods, they fit model use all predictors. Say we still have p predictors, and it will do the model in a way that it will constrain the coefficients estimates. So basically, it will shrink the coefficients towards zero. It turns out this shrinkage, shrinking the estimates, it will reduce the variance. Remember what the variance means in modeling? Say when we do when we model the data, when we do the modeling with training data, we get our estimates. But when we change the training data a little bit, your estimates could change a lot. That would impact the your testing set, prediction error, etc. So you change your data a little bit, it will change your model a lot. So that what we mean by it has big variance when we do the modeling. And the ridge regression and the lasso are the two we're going to talk about today. So if you still remember, when we do the least square estimate, we are minimizing the residual sum of square. So it's a summation of the squared residuals. And for ridge regression, we will minimize a slightly different sum. We still have this RSS. It will plus a penalty term, which is a tuning parameter lambda times the summation of the squared coefficients. Okay. Remember this J is from 1 to P, so we are only focusing on those coefficients beside the intercept because beta 0 is not included here. Okay, and this tuning parameter will be determined separately from those betas, from those coefficients. The second term is a shrinkage penalty, and we will minimize this thing along with this RSS. So we are minimizing this whole thing, the penalty will be small when the coefficients, they are close to zero, okay, because they are squared sum. So when they are small, their square is small and the summation is small. And the effect, this penalty term, the effect it has is shrinking the estimates towards zero. So because we're minimizing this thing. So we want this small and this is also small. So this being small means we're dragging those betas to zero. And this tuning parameter would control which of these two terms would have more impact. So which of these two would have more impact? So when lambda equal to 0, it will give the least square estimates just by minimizing the residual sum square. It's just what we used before for linear simple regression. And when lambda goes to infinity, it will increase the impact of the penalty term, right? Because their coefficients is getting bigger, it multiplies a bigger thing. So the penalty will be will be larger, and the coefficients estimates would approach 0. And this lambda is often chosen by doing cross-validation. Remember how we do cross-validation? We talked about that in which week? So when we talk about those resampling methods to evaluating your model. Yeah, so this lambda, you pick lambda by doing cross-validation. Yeah, I mentioned those penalty is not applied to the intercept term. Okay, we are only put penalty on getting like bigger coefficients for the predictors. So it's important to notice that the coefficients, they are no longer scale equivalent. What is scale equivalent? So remember when we do the least square estimate, if we increase our predictor xj by a factor of c, like multiplying xj by c, it would just make our coefficient estimate beta j to be different by a factor of 1 over c. So in that way, xj times beta j, they're still being the same. But the coefficients in ridge regression, they can change by some other things, like including the lambda, and it will depend on the scaling of other variables. Say if you change other variables by like some factors, and the coefficients of beta j, the coefficients for xj, the beta j will also change because we have more moving pieces here in ridge regression. Well, a good way to avoid this problem is just to standardize our data. So we would just standardize the predictor before doing the regression. Oh, right. Well, standardization, if you still remember, we just take our variable divided by the standard deviation of it. So this is the sample estimation of the standard deviation of this xij. So we get our new variables xij tilde. So basically we are doing a transformation before we do the ridge regression. To overcome this scaling problem. Because after this standardization, all the variables, all your standardized predictors would have the same variance being 1. Okay, so we will do the standardization first and then do the ridge regression. So let's talk about the coefficients a little bit, like how it looks like. So as you may imagine, the coefficients we selected, it will vary as a function of lambda. Remember, we have that lambda being a tuning parameter. And you will often see something like this to show you like when lambda is changing, like how the standardized coefficients will change. By the way, this is an example taken from the book of ISLR book. It shows you like when you change your lambda, how the values of those coefficients will change. And it shows when lambda goes up and those coefficients are getting closer to 0, right? Because in the middle is 0. So yeah, you will often see the plots like that to display how the values of the coefficients will change as the penalty change. So yeah, we have 2 plots here. This one have lambda, the tuning parameter, on the x-axis, and this one have this ratio on the x-axis. So let's talk about this ratio a little bit before we look at it. So this beta lambda r is the vector of the ridge regression coefficients. So this r denotes ridge regression, and lambda is because this beta will change depending on lambda. So we will use lambda as a subscription. In this notation, and this beta hat, remember here in the denominator, we have this beta hat. That's the vector of the least square coefficients. So basically the estimates you get from simple linear regression, you do the least squares, minimizing only the residual sum squares. And this, this thing, it's called L2 norm of beta, and which is the square root of the sum of the squared elements. So this L2 norm of beta is just you do the summation of the beta squared and then take their square root. So that's the L2 norm, and it measures the distance of beta from 0. Okay. Yeah, we mentioned by looking at like this plot, when when the lambda increase, the L2 norm of this beta lambda r would decrease because they basically goes to 0. They're getting closer and closer to 0. So this L2 norm will decrease, and the ratio, so this ratio will just goes to 1 when lambda is 0. Okay, so when lambda is 0, remember the ridge regression would basically become the simple linear regression, where we can get the estimates by least square methods. So they're basically the same. So the ratio is 1. And when lambda goes to infinity, so lambda goes to infinity, everything goes to 0, right? So those beta r, they are basically 0, and this ratio would definitely be 0. Okay. I like the one on the left better. It just shows you like how the tuning parameter would impact the coefficients, like how many coefficients are really important in the model, like when they have big coefficients. So yeah, this is the regression with the tuning parameter lambda. As you may notice, like I said, like the shrinkage methods, they are shrinking the coefficients towards 0. So particular for this ridge regression, it will never, like they never goes exactly 0, okay, unless you get like lambda goes to infinity. So it's just shrinking the coefficients smaller and smaller, closer and closer to 0. So that's what the ridge regression does. Okay, why we are doing this, why we use this ridge regression. I mentioned there is, what did I mention? Well, anyway, the ridge regression will use the bias and variance trade-off. Remember the mean squared error where we use to measure how good a model is. This mean square error is the summation of variance and the squared bias. Sorry. So basically, well, let's look at this plot first. So we have plot the bias, the squared bias, and the variance. So the squared bias, the squared bias is this black line. And this green line is the variance. So you notice when we have lambda increase, the bias would just goes up, and the variance goes down. Yeah, the variance goes down. Oh, right. So lambda increase, the flexibility of the fit decrease, because when lambda increase, it basically get more penalty on your coefficients. So those coefficients will get smaller and smaller, and the flexibility will just decrease, so that the variance will decrease. And we said we saw this bias is increasing. So this plot is just showing you that you are getting a decrease in the variance of your prediction at the cost of an increase in bias. So it's a trade-off. We we sacrifice the bias by getting a lower variance. So that's what the ridge regression is doing that, and that's why we use ridge regression just to reduce the variance of the modeling. Oh yeah, this is basically repeating the same information from the previous slides. So when so when lambda is 0, like on this very left side, we have no bias. The bias is small, and the variance is high, is at the highest level. And when lambda increase, so does this bias increase and the variance decrease. And when they cross, when these two cross, that's where we have the lowest mean squared error. So this purple line is the mean squared error, and this is when it's the lowest. So, and when these two are equal, like at here, we have the lowest mean square error, which is minimized. And this plot on the right hand side, it's passing the same information but use a different sort of format, because we are using the ratio of the L2 norm of the ridge regression coefficients and the L2 norm of the mean squared errors. The least square estimates. Okay. Still, I like this one better. You can just focus on this one. So again, why we do this ridge regression? So when is the best situation to use ridge regression? So I wrote here, ridge regression is ideal when we have when the least square estimates have large variance, and this will often happen when we have as many predictors and as variables. So so when we have too many predictors, the LLC would tend to have large variance, and especially when we have more predictors than our data size p greater than n, the least square is no longer unique. Least square estimates no longer unique, but we can still use ridge regression to get a good model. Okay, and also ridge regression would have substantial computational advantage over the best subset selection. Remember, when we do the best subset selection, we have to compare the model, like 2 to the power of p models, to get our best model, right, out of that many models. But the ridge regression is way faster comparing to the best subset selections. And of course, it would also have its disadvantage. And I mentioned a bit about this. The ridge regression, it will always include all the variables. So even though we are shrinking those coefficients towards 0, it will not set them to exactly being 0 unless we have this lambda being infinity. Okay, so normally when you fit a ridge regression, when you have p variables, the final model will still have p predictors. Just some of them will just be small, really small. Well, this would not affect the prediction accuracy, but the problem is when you have big model, when you have many predictors in your model, it's hard to interpret. So this problem, it will cause the issue when your goal is to do a model interpretation, especially when p is large. Okay. So basically, making lambda large, it will shrink the value of the coefficients, but does not fully exclude any. Okay, so this is the ridge regression. And we will talk about lasso and how it will overcome the problem. that ridge regression would have. Okay.